Okay, so in this chapter, we'll do electric potentials. Okay. So let me first set you guys up because it's a little complicated. Okay, so you guys saw this is, I'm just giving you a little review. Okay. If you have an object moving in a straight line and a constant force acts on it, the work done by this force when on this object when it moves from here to there is equal to work done is this dot product. Okay. Let's say if an object moves in a general trajectory from this initial point to this final point, okay. So what you can do is you can use this formula for this general trajectory. You can break that trajectory into little chunks, calculate the work done in each little chunk. The force can vary and all that. And in this general case, the work done is this line integral. Okay. All right. So now we'll do it in this context. So you've seen this. So let's say you have a bunch of charges. What do the charges do? They produce an electric field. And let's say this is the electric field in this region. I'm just drawing a random field. Okay. This doesn't even look like it's going to be related to this charge, but let's say this charge distribution produces this electric field. Okay. And then what you do is you put a positive charge. Okay. So and then this charge goes from here to there. Okay. And so as long as these charges are not moving and this electric field is not time dependent, yeah. So the work done is the force, which is the charge times the electric field, and ds. Okay, so the work done is this line integral. The same as before, except that the force is Q times E times ds. Okay. That's how you would calculate the work done by this electric field on this charge when it moves from here to there. Okay. And it turns out that this work done is independent of the path. So it doesn't matter how you go. If you get there from like that, the work done, this integral turns out to be the same. Okay? And so the electric field, okay, the electrostatic force is a conservative force. All that means is this line integral is path independent. Okay. And so what that means is you can find a scalar function. The line integral is just the value of that function at the end point minus the value of the function at the initial point. And it turns out that we want to define that with a negative sign. Okay. So all that it means is when the force is a conservative force, this line integral is easy to do. Well, in fact, the value of the line integral is just the difference in this function. Okay. U is called the potential energy function. Now, you will see this in a second. We will also define something called the electric potential function, and I'll tell you why. The electric potential function is defined as follows. So change in electric potential, change in potential energy function divided by Q. It's potential energy per unit charge. That is VF minus V initial is UF minus U initial divided by Q. All right, so we'll study all of this in this chapter. Okay. All right, let me summarize this again. Okay. Okay, so when a force acts on a particle, and if the particle travels along a general trajectory like this, the work done by this force on that particle is given by this line integral. Okay. Now, in general, this line integral is hard to calculate. So if this was you pushing a cart in a supermarket, that line integral would be hard to do. Okay. In practice, you couldn't do it. But let's say if you have a bunch of static charges, they'll produce an electric field in the room. And then if this electric field will have a force on a charge, and if this charge moves along this trajectory, there is the work done by the electric field. Okay. The force on the charge is Q times E. So the work done is this line integral. And in this special case, for the electrostatic fields, it turns out that this integral is easy to do. It is path independent. The answer depends only on the initial point and the final point. Okay? And so that line integral, that work done, is the difference in a function, the potential energy function. It's negative of the change in potential energy. Okay? So you just have to figure out this potential energy function, and you just calculate the potential energy at the final point minus the potential energy at the initial point, and negative of that gives you the work done. Okay? All right. Now it'll turn out that, so that's the potential energy function. It will turn out that it's more, you want to define something called electric potential function, which is just the potential energy divided by charge. So change in electric potential is change in potential energy divided by charge, the charge that is moving. So electric potential is the potential energy per unit charge. Okay. All right, so we'll learn all of this stuff. All right, so again, like I said, there are two terms, and you want to be careful. Electric potential energy, denoted by U, and electric potential, which is the title of the chapter, which is denoted by V, and delta V, change in V, is equal to delta U by Q. Okay? And I'll show you why we define that. Okay, I'm just going to briefly mention this. This is something that you would study if you're a physics major, well, an electrical engineer or a physics major or something like that. You can almost say that almost all of electrical engineering is based on these 4 or 5 equations. Okay, so that's a pretty powerful statement. Okay. a lot of what you study in electrical engineering is based on these equations. Okay. All right, what these guys say is, okay, so these equations, in these equations, what you do is the right-hand side is the cause. Okay, you don't have to understand these equations. I'm just telling you a few things about it. The right-hand side is the cause, the left-hand side is the effect. Okay, so you guys saw, for instance, charges produce electric fields. Okay, so this is charge density. Charge density is producing electric fields. Okay, and the form of the equation relates their configurations. Okay, so that's what that equation is telling you. Okay, so for instance, you guys remember, if I place a positive charge, how does the electric field look like? What is the electric field around it?
Points away from it, right?
Right, okay. And this form of the equation tells you that. Okay, this equation will tell you that. So in a later chapter, you'll learn this. Okay, if you get the charge moving, what you'll learn is it produces a magnetic field around it like that. Magnetic fields are denoted by B. So, for instance, here, if your thumb points in the direction of the motion of the charge, the magnetic fields point like that. And this equation tells you that. Okay, but again, we'll come to that. So charges produce electric field. Okay, what this equation is telling you is, see, you have positive and negative charges, but you don't have such charges for magnetism. So if you ever go to a store and buy a North Pole, they'll always sell you a South Pole with it. You just can't buy a North Pole or a South Pole by itself. Okay, those things are called monopoles. But anyway, so that's what this equation is telling you. What is this equation telling you? Can anybody read that equation? And tell me in words, what is this equation telling you? So just tell me cause and effect. What is the cause and what is the effect? Okay, so time varying magnetic fields is the cause. Okay, so if you have time varying magnetic fields, that produces electric fields. So here's a second source of electric field. Charges produce electric fields, and time varying magnetic fields produce electric fields. Okay, this equation is a basis of thousands of applications in your life. Okay, this is how microphones work, this is how speakers work, this is how electric guitars work, this is how that electric sitar works. Okay, so we'll learn that. Okay, again, time varying magnetic fields produce electric fields. This equation is telling you this is current density. Moving charges produce magnetic fields. Okay, so that's an entire chapter. Okay, again, so we'll be devoting entire chapters to just each piece of the equation. Okay, we'll denote an entire chapter to this. Currents producing magnetic fields. Time varying electric fields producing magnetic fields. Okay, you don't have to know any of that. I was just making you aware of it, showing you that there's value in learning to read equations. Okay. All right. So let's become aware of one thing. Okay, so let's say this thing shows you an electric field in this direction. And the way you can produce this electric field is, for instance, if you smear the ceiling evenly with positive charges and the floor evenly with negative charges, you'll have an electric field pointing downwards from the ceiling to the floor. Okay. Now let's see if you remember this. What happens if I put a positive charge here? Very good, Eli. The force, remember the force equation is Q times E. And if the charge is positive, the force is in the same direction as the electric field. Okay, so the force on a positive charge is downward. What if the charge is negative? What if I put an electron instead? Very good, Eli. The force is in that direction. All right, so here's what we've done. Okay, if the electric field is pointing downwards, okay, and I let go of a positive charge, it will fall downward. If I let go of a negative charge, it will fall upward. Okay. How about this mass? If I take a mass and if I let go of this, which way will it fall? It will fall downward. Okay. There's only one kind of mass. There's no negative mass. Okay, so it falls towards the gravitational field. Because we have two kinds of charges, okay, the positive charge falls downward and a negative charge falls upward. Okay. All right, so now go ahead. Did you have a question?
Oh, no, sorry, I was just scratching.
Okay.
My forehead.
Okay, as this guy falls, his kinetic energy is increasing. What is decreasing?
Potential energy.
Its potential energy is decreasing. Okay, so as this positive charge falls, as he falls, his potential energy is decreasing, okay, and kinetic energy is increasing. How about this guy, negative charge? He is falling. His potential energy is decreasing in that direction. Okay? So if he fell this way, his potential energy would increase. Okay? See, in the case of the mass, potential energy was decreasing in this direction. Okay? But for the positive charge, potential energy is decreasing here. For the negative charge, the potential energy is increasing as it goes down here. And we don't like that. So we want to define something that is charge independent. And that's what this is. Electric potential is potential energy. So change in electric potential is change in potential energy divided by the charge. And that will remove the charge dependence. So as the positive charge falls, its potential energy is decreasing divided by this gives you a decrease in electric potential. As the negative charge, if you bring the negative charge in this direction, okay, the potential energy has increased. This is positive, but divided by a negative charge gives you a decrease in electric potential. Okay, so this quantity is charge independent. This is charge dependent. This is charge independent. So if you followed that argument, you saw that V decreases in the direction of E. So electric potential is decreasing in this direction. Yep. So which way does the electric field point? In the direction in which V is decreasing. Okay. All right, so what are conservative forces? work done by these forces is path independent. Okay, so work done by these forces is path independent. Okay. So for instance, if you saw this in the first semester as well. So let's say the gravity is a conservative force. Work done by gravity along this slide and this slide is the same. So if they were frictionless, that you would come out with the same speed along both those rides. Okay? Because the work done by gravity is path independent. Okay? So with conservative forces, you can associate the concept of potential energy. So again, work done by conservative forces is potential energy, difference in potential energy, and we use a negative sign for convenience, okay? So only with conservative forces can you do that. So if you're pushing a cart in a supermarket, the work done cannot be written like that. The work done by friction forces cannot be written like that. The work done by rockets cannot be written like that. The work done by your car engine cannot be written like that. Okay? In fact, which are the conservative forces? Do you know what are the conservative forces? We've told you only 3 conservative forces. Very good. Very good, my friend. Spring force. The other 2?
Gravitational force?
Oh, very good. We already talked about that. Gravity. And the third one?
CH07.
Very good. So, electrostatic spring force. Yeah. Okay, those are the only 3 conservative forces. All right, so I'll illustrate that for you guys in a very simple case. Okay, the force exerted by the electric field is conservative. Okay, so the work done is path independent. So I'll show that to you. Okay, so let's say we'll show that to you for a constant electric field. Okay, it's true even if the electric field is changing spatially, but we'll show it for you for a constant electric field. Okay, so here's the constant electric field. Okay, and I'll show you, we'll take a positive charge from this initial point to that point, and there's one path here, and we'll take that charge along this path as well. Okay, so what are we trying to prove? That the work done along this path should equal the work done along this path. Okay, and then it's a conservative force. So then it's potentially a conservative force. Okay, so the work done in going from initial to final point is this integral. Okay, and there's Q. Okay, so the proof is all right. Well, what we're doing is the electric field is constant, so that comes out. The integral. So it's QE dotted with sum of ds. What is ds? ds are these line elements. Okay. So for this path, this ds plus this is that vector S. For this path, it's this vector plus this vector plus this vector plus this, and it's the same. The sum of all those little elements is that. Okay. So it's QE dot S, no matter what path you take. Okay? So it's path independent. So the work done is by this force, it's a conservative force. Okay? So the work done, and so this is true even in the general case, the work done is path independent, and so we define a potential energy function U, and it's equal to negative change in potential energy. Okay? So you saw that for, oops, I showed you that the work done by this constant electric field is just E dot S, okay? So when the electric field is constant, okay, so when the electric field is constant, the work done is E dot S, okay? So the work done is delta U, and so delta U is minus W, which is minus Q E dot S. Okay. And that's what this is telling you. So change in potential energy, and change in potential energy is U final minus U initial is equal to that, is minus Q dot S. So if this is positive, okay, so if the charge is falling in the direction of the electric field, this will be positive. The dot product will be positive. And if the charge is positive, a positive charge loses potential energy as it falls in the direction of the electric field. That's what this equation is saying. Okay? So we'll keep it simple. Here is S, here is E. Okay. E dot S is positive when the charge is falling in the direction of the electric field, and if the charge is positive, then it's losing potential energy. If the charge is negative, it's gaining potential energy. Yep. So negative charges gain electric potential energy when they move in the direction of the field. Okay. All right. The units in which electric potential is measured is called a volt, after Mr. Volt. Okay. All right. So we define this electric potential because this guy is dependent on the charge. So if you divide that by charge, this quantity becomes charge independent. Okay. So the change in electric potential, the difference in the electric potential between 2 points, change in electric potential is equal to change in potential energy divided by Q. And of course, this is negative of the work done. Okay. So change in electric potential is this line integral. Okay. Again, this has a lot of math, I realize, but we'll remember simple things. Okay. So if you do this line integral and going from here to there, if you do this line integral, what you find is V final minus V initial is what you get. And that's what this line integral will tell you. So if the potential is 15 volts here and 3 volts here, 15 minus 3, 12 volts is what you get for this value of this line integral. Okay. All right. So the units for volts are volts after Mr. Volt, and it's so electric potential, the units are volts, and potential energy is measured in joules, and that's in coulombs. So joules divided by coulomb is a volt. Okay. Volt is also, this is in meters. So if you divide that by meters, volt per meter gives you the units for electric field. And the units for electric field were also Newton per coulomb. So 1 volt per meter is also equal to 1 Newton per coulomb. Okay. Okay, so here's one more formula, and then we'll be done with all the formulae. And I'll explain stuff in pictures again. In a uniform electric field, again, what do we mean by a uniform electric field? What does that mean?
The charge is the same at every spot?
The electric field is the same vector at every spot, okay? So its magnitude and direction is not changing. So in this room, again, how would you make the field uniform? You can smear the ceiling evenly with positive charge, smear the floor evenly with positive charge, and every point in this room, the electric field will be pointing down and have the same magnitude. That would be a uniform electric field, okay? In a uniform electric field, the change in potential, final potential minus initial potential, is just the dot product of the electric field times the displacement. Okay. So let's say the electric field is uniform and pointing like this. Okay. So let's say this is the initial point and that's the final point. Okay. The electric field is like that, and there is S. So the electric field is pointing like this. It's uniform, and you took a charge and a charge moved in this direction, or you moved in that direction. What is the change in electric potential? 0. Very good. Okay. So you've learned a very important fact. Okay. The potential all along this point, these points are change is 0, so they're equal. This surface is called an equipotential surface. Okay, so very important. Equipotential surface. And notice this, electric fields are perpendicular to equipotential surfaces. Okay, so let me show you a picture. Did you guys understand that? Okay, so here are equipotential surfaces. All it is saying is on this surface everywhere it's 9 volts. On this surface everywhere it's 8 volts. Okay, so if you wanted to find the electric field at that point, it's perpendicular to that surface. Okay. All right, so here's a surface. Here's a surface. This is at 9 volts. I want to find the electric field at this point. It's perpendicular to this surface. But this surface has how many perpendiculars? Well, at this point it has 2. One in this direction and one in that direction. So which way is the electric field pointing? It's pointing in the direction of decreasing potential. Okay? So it's pointing in that direction. Okay? So let's say if this is the surface, this is the surface, this is 10 volts, 9 volts, and 11 volts. So at this point, the electric field is pointing like that. Okay, at this point, it's pointing like this, and so on. Okay? The electric field is always pointing perpendicular to the surface, and it's pointing in the direction of decreasing potential. Okay? All right, so this shows you, so here are 2 positive charges, and these are the electric field lines, and these are the equipotential surfaces. Okay? And at every location, the electric field is pointing that way. Okay. So what is this guy? This is a positive charge and an equal negative charge. What is it called? It's got a special, very good. It's a dipole. And these are equipotential surfaces around the dipole. And you see the electric fields are always perpendicular to the equipotential surfaces. Okay? So electric field lines point in the direction of decreasing potential. All right, so here's an electric field, now that we've done. Okay, so I want you to make sure that you understand this. Electron volt, it's a unit of energy. What other units of energy do you know? I'm sorry? Very good, joules, okay. I'm sorry? That's coulombs, that's the unit of charge, that's not a unit of energy. So joules, that's all we've talked about. Ergs is a CGS unit of, okay, and calorie is another unit that you've learned, and so on, okay. This is a unit of energy as well, okay. All right, so let's make sure we understand this, okay. So here's an electric field. Okay, so I'm going to say V electric potential. Where is electric potential? Okay, so at which point is the electric potential higher? The top one, very good. So this is high and this is low, okay? So we learned this. Okay, so let's say this is 10 volts and this is 9 volts, okay? Let's take a proton and release it there. Which way will it fall? Down, okay? Its potential energy is decreasing, okay? So change in potential energy is Q times change in potential, okay? So electric potential decreased, so its potential energy decreased, okay? Okay, so when this guy, I dropped this, its potential energy decreased. What happened to its kinetic energy? It increased, okay? All right, in this case, let's say, is the charge of the proton and the electron the same? Yeah, the magnitude of the charge is the same. If I let go of an electron, what will happen? It'll fall up, okay? What will be the change in potential energy of the electron? Its charge is the same, it falls through the same potential. Its change in potential energy will be the same, okay? So the energy gained by 1 coulomb of charge, not 1 coulomb, 1 charge, 1 unit of charge times 1 volt is called an electron volt. So when an electron falls through 1 volt, the energy it gains is called an electron volt. When a proton falls through 1 volt, the energy it gains is 1 electron volt. So if a calcium ion falls, a calcium ion with 2 charges falls through 1 volt, how many electron volts will it gain?
2.
2 electron volts, very good, okay? All right, so an electron volt is that many joules. All right, you guys know units of distance?
Meters.
I'm sorry?
Meters.
Meters, what else? Huh?
Empirical feet, go feet.
Yeah, kilometers,
Kilometers.
light years,
Light.
centimeters, micrometers, nanometers. Why do we define all these different units? Okay, so if you want to describe somebody's height, this is a good unit. If you want to describe the distance from here to Jacksonville, that's a good unit. You want to describe the distance, the diameter of our galaxy, this is a good unit. You want to describe the size of a cell, that's a good unit. That's the size of an atom, that's a good unit. Similarly, okay, when you jump from the table down, that's a good unit. Okay. If you're trying to describe the energy levels of an atom, that is a good unit. Okay, so let me give you an example. And I don't know if I want to promise $1, but we'll think about it. So we mentioned this before in class. Okay. Can you ionize? What does ionization mean?
The removal or addition of electron.
I'm sorry?
The removal or addition of electron.
Removal, not,
Removal.
yeah. Okay, so you can obviously remove this and send it to infinity. Okay, so this is a hydrogen atom. What is the ionization energy of, yeah?
13.6
Yeah,
electron
I'm
volts.
sorry. 13.6.
You've taken enough of my money, I'm not giving you anymore. Very good. That's exactly what I was looking for, okay?
As soon as you
13.6.
drew the picture, I already knew it was.
All right. So you see, so when you, in chemical reactions, that's the kind of energies that are involved. Okay. So what is a chemical reaction? You're just rearranging outermost electrons. Okay. And that's the kind of energy you need. You want to pick an electron from here and give it to him, and so on. Okay? So in this business, that's a very good unit of energy. Okay, and if you want it in joules, that's 1.6 times 10 to the minus 9 joules. Okay. Okay. What is this guy? This is 1,000,000 electron volts. Okay, so let's get back to this guy. All right. Maybe a soda to somebody who will tell me what this guy is. It's a hydrogen. Very good. It's a hydrogen isotope. It's deuterium. Okay. So to remove this electron, you need 13.6 electron volts. Can I pull this guy out? Yes, of course. In physics, you can do everything. You can pull everything apart. You'll need about 2 million electron volts. 1,000,000 times more energy. That's why nuclear energy is so much more valuable. Okay? You can mess around with electron with chump change. Okay? So you mess around with the nucleus, now you gotta need this kind of energy.
Is it because of the strong force?
Very good, very good. I might buy you that soda after all. Yeah. All right, so to mess with the nucleus. Well, you're not happy with that. I'm going to mess with the neutron. Can I break that apart? Yeah, well, so it is made of quarks. You can make quark soup, but we've never seen that by itself. But to mess with this guy, you need more energy than this. Okay? And at the Large Hadron Colliders, they have energies of 1 trillion electron volt, 1,000,000 times greater than that. So they take protons and collide them together at 1 trillion electron volts. You get a mush. Okay, you'll get a quark gluon soup, and they combine again, and you get new particles coming in. Okay. So the point is, okay, I mean, all these different fields are very complex, and people spend lifetimes studying these. Okay. The energy scales are different. So if you live here, that can be your calling card. So if you say, I live in the MeV range, we know you're a nuclear physicist. Okay. If you live in the TeV world, you're a particle physicist. And so on. Okay? Okay, you guys understand what an equipotential surface is? Okay? And electric field lines are perpendicular to equipotential surfaces. Okay? Have you guys done spherical polar coordinates? Okay, are you in Calc 3?
You just finished all three.
Huh?
You already finished all three.
Oh, okay.
Yeah.
Okay, so this will give you the electric potential for a point charge. Okay, so the electric potential for a point charge is, if you have a point charge, the electric potential at that distance, it's a scalar quantity. This is the Coulomb's constant. This is the charge divided by the distance. Okay, so if the charge is positive, the electric potential is positive at that point. If the charge is negative, the electric potential is negative. Okay, and as you go further and further away, the potential decreases. Okay, and the value of the potential decreases. Okay, so this is a infinitesimal displacement. In Cartesian coordinates, it's written like so. And if you don't understand it, don't worry about this. We don't need to go through the proof. I'm just showing it to you. Okay. If you write it in spherical polar coordinates, little displacement is just that, ds. Okay. So what? So, oops. This ds, there is I, J, K, is written in terms of I, J, K like that. Okay. That displacement also can be written in terms of r hat. R hat is a vector. If you're at this location, r hat is a vector that is pointing away from the origin, unit vector pointing away from the origin, and so on. R d theta, theta hat, plus r sine theta, d phi, phi hat. Again, you learned this in Calc 3. If you haven't seen it, don't worry about it. It's just a little displacement. Okay. If you use different coordinate system, you're just expressing this vector in this language. You're expressing the same vector in a different language. It's the same vector, that's all. Okay? I, J, K are unit vectors. R hat, theta hat, and phi hat are unit vectors. Okay? Okay, the reason I'm doing that is the following. All right, so what we're going to show you is, we already saw this expression. The potential at B minus potential at A is this line integral from A to B, negative of this line integral. Okay, from a point charge, there is the electric field. And I'm going to substitute ds in spherical polar coordinates. Okay, so that's negative kq r square r hat dotted with ds. ds is dr r hat plus r d theta theta hat plus r sine theta d phi phi hat. And the point is r dot r is 1, r dot theta hat is 0, r dot phi hat is 0. So those terms drop off, and the only thing that is left is kq divided by r squared dr. And this integral is easy to do. Okay. You might notice that we only show you easy stuff in the classroom. Okay. Yeah. So this integral is easy to do, and that integral is that. Okay, go home and look at it. So the electric potential due to a point charge at a distance r is given by that. If Q is positive, okay, so if you have a positive charge, the potential is positive. So if this is 10 volts, this might be what would be the potential? Lower, 9 volts and so on. Okay? That's what this is giving you. From a negative charge, the potential is, so this is 10 volts, and this is minus, it's bigger, 15 volts and so on. Okay? And so on. Okay. All right, so that's what I want you to remember. The electric potential from a point charge is given by that. A positive charge produces a positive potential, and a negative charge produces negative potential. Okay, so if you have several charges, if you want to calculate the potential at any point, just add up the potential due to each charge. So the potential at this point is the potential due to this guy plus the potential due to this guy and so on. Okay. So let's look at this diagram. So here are 4 charges. Okay. And what is this guy saying? What is this diagram saying? Mm-hmm.
The equidistant, the equal, like the whole line is equal to.
Equipotential. Very good, my friend. So that's an equipotential surface. Okay. Now I'm going to make up another equipotential surface. I'm not sure if this is correct. Okay, so I just am making it up. Let's say this is a 340 volt surface. At this point, which way is the electric field pointing? Very good. You know that it's perpendicular to the surface and it points in the direction of decreasing potential. At this point, it's pointing in this direction. At this point, it's pointing. Okay? So that's very useful information. Okay? Once you know equipotential surfaces, at every point you can calculate the electric field. Okay? In fact, the electric field, the magnitude of the electric field, now you know the direction of the electric field is the change in potential divided by the distance over which that change happens. So if this 10 volts, in this case, if this is 10 volts, if it happened over 1 centimeters, okay, it would be 10 volt divided by 10 to the minus 2 meters, which is 1,000 volts per meter. Anybody remember what do you need to create lightning? I'm sorry? Very good, 3 million volt per meter. 3 million volt per meter. Okay. Okay, so 3,000 volt per millimeter. That will create lightning as well. So that's roughly the gap, spark gap in your spark plugs. So every time, how many times are you creating that spark in your spark plug?
Depends on the RPM.
Yeah, it depends on the RPM. I mean, if 3,000 RPM, that's 3,000 times 4 cylinders. Yeah, 4 cylinders. So 12,000 times a second. Okay, you're creating sparks. All right. So this is the electric potential of a dipole. Here's a positive charge, here's a negative charge. Okay, this is the dipole. Again, a dipole is a charge separation. Naturally occurring dipoles have very small charge separations. Can you tell me a naturally occurring dipole?
Water.
Very good, my friend. Okay. So here is a water molecule. This guy is greedy for electrons. So the oxygen guy is greedy for electrons, and this is the center of positive charge. It's very hard to separate charges, so this distance is not that great. Okay, so for most organic molecules and stuff like that, or for most molecules, the charge centers are right on top of each other. Okay, and and they don't have any dipoles, okay? And this dipole moment is a very important thing, you know. So naturally occurring dipoles have very small charge separations, okay? Now, it turns out that, see, from a point charge, the potential falls off as 1 over r. From a dipole, the potential falls off as 1 over r squared. Okay? Because the further out you are, this will start appearing as a neutral charge. So the potential is falling off faster. If you have a cloud of charge, to find the potential at this point, you do this volume integral. Okay? You break this up into little charges, point charges. The potential due to this guy is k d cubed by r, and then just sum them all. Okay, if you have a conductor, and we saw that if you throw a bunch of charges on the conductor, they'll lie on the surface. Okay. How do the charges distribute?
Uniformly?
If it's a sphere, it'll go uniformly. What is it that they're trying to do? What is it that you want?
Be as far away from each other as possible.
That's one thing. Very good.
At the surface.
They're at the surface. Another thing. They arrange themselves such that the electric field inside is 0. Okay, so those are the 3 important things. Okay, and in a conductor, so they've arranged themselves such that the electric field near the surface is perpendicular to the surface. Okay, so let's see, let's find the potential difference between these 2 points. Okay, the potential difference between these 2 points is negative of this line integral, E dot ds. Let's say we go along this path, electric field everywhere is 0, so this will work out to be 0. Even if you come along the surface, E is there and ds is like that is 0. So this point is at the same potential at that point. So everywhere on the surface of a conductor, the potential is the same. Okay, so if this point is at 10 volts, everywhere on the surface it's 10 volts. Well, okay, what about this point? Again, you do this line integral everywhere inside, E is 0, this would be 0. So if this is at 10 volts, this is at 10 volts. So a conductor is an equipotential volume. If this guy is at 10 volts, everywhere on that conductor it's 10 volts. Okay. So that's what it's showing you here. So everywhere inside the conductor, it's this. Yeah. So here's an interesting diagram. Okay, so here is a constant electric field. And how do you do this? You smear this wall with positive charges, and you smear this wall with negative charges. Here's a uniform electric field. And now, if you go and bring a chunk of metal and put it in here, this chunk of metal will distort this field, and the distorted field will be like that. And again, why did it distort? Because it wants to maintain a 0 electric field inside. So it redistributes the charges. Well, this chunk of metal was neutral to begin with. You get a bunch of positive charge here and equal negative charge here. Yeah? Okay. So a metal will distort the electric field around it. Yeah?
Once you move from the charge, will it stay that way, or will it snap back to what it was?
I'm sorry, say that again.
Once you induce the charges and it's removed from the electric field, will it stay that way, or will it?
Yeah, so if you, okay, very good question. Now, let's say Courtney asks, if you remove this piece of metal outside the electric field, it'll go back to its neutral state. This electric field will go back to its original state. Okay. So let's see what happens. So the electric field inside is 0. It turns out that if you have a hollow cylinder as well, it doesn't matter. if you have an external electric field, what happens is you will have charge redistribution such that the electric field is zero in this entire volume, even here. And this is called a Faraday's cage because it's shielding you from any external field. So you can sit inside here. Okay, this electric field can be strong enough to have lightning, but you're perfectly safe. Yep.
So let's say,
Mm-hmm.
You can go first.
let's say that
Mhm.
in Google, I'm inside that box,
Mm-hmm.
and a lightning hits, I'll be protected.
You'll be protected.
What if I decide to touch both ends of the box?
So you can touch this end of the box, but you can't touch the outside. And I got to experience that in the summer. I tried looking for the picture before I came, but I couldn't find the picture. Yep.
So if Iron Man got struck by lightning, he would be fine? Because he's in a metal suit.
Yeah.
But it also has a battery in it.
What's that? No, well, okay, so, well, he'd better be walking on the ground. You want the charge leaking out. Well, okay, so maybe even if he's flying, if the electric field is strong enough, the lightning will go through him, and hopefully the air is charged. Okay. Yep. Yep. All right, I want you to understand this. Well, I want you to understand everything, but I know this lecture has been long, but do you guys remember what a gradient is?
It's a circle cut into 400 degrees.
No, I'm talking about.
Partials of
I'm sorry?
the partials of a three-dimensional.
Very good, very good. So for a scalar valued function, okay, I'm just going to make up an example. X squared y cubed z4. What does this do? At every point, it's associating a value, a scalar value. That's what a scalar valued function is. So it'll spit out a number, okay, at every point. Then you can ask the question. So let's say this is 100, 101, 102, 100, and so on, all kinds of numbers. You ask the question, in which direction is it increasing the fastest? That's a legitimate question, okay? So for instance, let's say in this room, this was the temperature in this region. And then you can ask, in which direction is the temperature increasing the fastest? Okay? That is given by the gradient of the function. Okay, so the gradient of the function is like Joe said, is del f by del x, I, plus del f by del y, j, plus del f by del z, k. All right, I don't know how to do this. What is del f by del x?
2x, y cubed, z.
Very good.
Three x squared, y squared, z squared.
Very good. So when you're doing partial derivatives, what you're doing is you're treating the other variables as constants. Okay? J plus hmm?
X squared, y cubed, 4z.
Okay. Okay, and what does this tell you? It tells you how the function is changing if you're moving along the x in the x direction. That's what del f by del x tells you. If you move along the y direction, that's what del f by del y tells you. And if you move along the z direction, that's what del f. Okay. Well, why do we calculate this? If this was the temperature, the gradient of the temperature tells you which direction the temperature is increasing the fastest. And heat will flow in the opposite direction. Okay? If that was pressure, pressure is increasing in that direction, and wind blows in the opposite direction. Okay? So that's the kind of stuff. So that's why you want to calculate the gradients. All right. I know Christina is falling asleep, so we'll just cut it short. All right. So the electric field is given in terms of the electric potential like that. It's gradient of the electric potential. Negative of the gradient of the electric potential. You already saw this. See, electric fields were perpendicular to equipotential surfaces, and they were pointing in the direction of decreasing potential. Okay, so so let's go back. So here's an equipotential surface, and potential is increasing in that direction. This is the direction in which electric gradient is pointing, and electric field is pointing in the opposite direction. Okay? Okay, so that's important. Okay. And again, that figures in many laws. So heat flows in the opposite direction of temperature gradient. Wind blows in the direction of pressure gradient. Very good. Diffusion happens in the direction of?
Concentration.
Very good, my friend. Very good. Concentration gradient. Okay, so diffusion occurs in the direction opposite to the concentration gradient. Okay. All right. So these are equipotential surfaces, and electric field point in the opposite direction. The potential energy between two charges is that, okay, U is potential energy K times Q1, Q2 divided by R. Okay. If you have a constellation of charges, the total potential energy is the potential energy of this pair plus this pair plus this pair. Okay, potential energy of all the independent pairs. Okay. We saw the electrostatic precipitator removes all the smoke particles, okay? And the way it does is, see, you apply 100,000 volts between pieces of wire and metal stuff, and here are smoke particles going through. This wire, which is negatively charged, connected to the negative electrode, is spitting out electrons, and these electrons stick to the smoke particles, which go and stick to the positive plate. Okay? And then you shake this up. So you can remove all the particulate matters. You can remove 99% of the particulate matter, but it costs you about 3 cents to every dollar you produce. Okay? So you had to make laws for people to comply with that thing, to spend that money. Will all vehicles be electric in the future? 50 years from now?
Is that a question or a statement?
And that's a question.
Oh.
She's not sleeping. Yes. No, so they'll all be. Okay, why do we want all electric vehicles? Well, anyway,
It's more efficient.
zero carbon footprint. Okay, that's the most important thing. Okay, so you produce electricity from sunlight, and they are more efficient as well. So they're 90% efficient. Okay, this just gives you the numbers. I'll just quickly go over the numbers. Okay, so I think this might be the cheapest version of the Tesla. Okay, so if you use 60% of the charge, So this is the battery size. That tells you how much energy there is. So kilowatt hour. This is a unit of power times time. Power is energy divided by time. So power times time is energy. So this tells you how much energy is packed in that battery. It's like telling you how large a gas tank is. Okay.
So do you calculate the total pollution of the vehicle by calculating like the pollution that goes into making it, and that's it?
Well, you're going to make it whether you're making an electric car or yeah.
But I mean, like lithium-ion cobalt mining is like the most destructive minings. So, no, I'm just saying, like, you're paying something, but you're paying for it upfront or in the long run.
Okay, no, I've been driving my car. Well, we won't get into that. Okay.
I'm just trying to like figure out like how would you calculate like its total actual efficiency versus an automobile versus looking at in a particular
Okay,
moment
so
versus like a lifetime. That's what I'm saying.
Okay, so the operational carbon footprint of an electric car is 0. The manufacturing carbon footprint would roughly be the same.
Yeah.
So for
I
instance,
mean, like mining, like I'm talking about like mining and stuff.
yeah, well, I mean, you have to mine for metals and all that kind of stuff when you're making your car and all that. I mean, do I have the precise number? No, but it's obvious if, okay, so my car has 300,000 miles on it. The carbon footprint of all that driving is way more than the carbon footprint of the manufacturing that went into the car. I can assure you that.
Oh, I was just interested. I've got no preference on either one. I wanted to know like how would you calculate overall? Because nothing's zero carbon in life.
Yeah. I mean, you see that I have trouble solving these simple little problems. That's a tough question, my friend. All right. So this is an energy pack. You're going to use 60% of that energy. Okay, so here's the calculation. A kilowatt is 1,000 watts. An hour is 3,600 seconds. Okay, so this much energy. Okay. Well, let me show you. 1 kilowatt hour is 1,000 watts. Watts is joules per second. An hour is 3,600 seconds. Oops. So 3.6 into 10 to the power 6 joules. 1 kilowatt hour is 4 million joules. See, this is what you pay your electricity bill by. This thing costs you 12 cents. 4 million joules of electricity costs you 12 cents. So look up your electric bill. Well, what can you do with this? A 100-watt bulb. You guys know what a 100-watt bulb is. 2 of those guys are 100 watts. Each one of those. What? Okay. So let's do this. 100 watts. A kilowatt this is a kilowatt and 1 hour. So you can burn 10 100-watt bulbs for 1 hour. That's what you can do with 1 kilowatt hour. Okay. Anyways, so that's the battery pack. That's how much energy you have. An electric car is 90% efficient. Okay. And with that 90% efficiency, you can get 103 megajoules of motion. This is the calculation for a gasoline, so that's a normal gasoline tank. When you burn 1 liter of gasoline, you get 35 megajoules of energy, heat, but the gasoline car is only 20% efficient. So that tank had that much energy, 20% of that. 20% is converted to motion, you get this much motion. Okay, so those are rough calculations. All right.